Good afternoon and welcome back to our AP Physics 1 review sessions. My name is Joshua Beck. I'm coming to you from Clayton, North Carolina. Today we're going to be focusing on one of our free response questions from an exam in 2018. Just keep in mind what we're trying to do is prep you guys for this 2020 exam. On this exam, you're going to see two different types of questions, but as you've seen, Greg and I have been going over a variety of different types of questions because built into the previous questions, you will have similar elements that you will see in a QQT and in a paragraph. So I'm going to go ahead and jump right into it today. We're starting with the 2018 free response question number 1. Greg posted this yesterday for you, so if you watched his lesson, you should have this question and you may have practiced it. We've even seen some people starting to submit some of their work to us to kind of take a look at or ask questions about, and that is great. That is one of the things that we are here for. So what I want to do is kind of go through this and give you an opportunity to see where maybe some of the common pitfalls are, maybe some mistakes that you made when you tried it, or as you go through this today, maybe this is your first time seeing it. As you go through this today, maybe I can help address some issues that maybe you might run into as you're going through this. So this particular question involves a couple different things. One of the things I like to do, just a quick mental exercise when I see a diagram on one of my free response questions, is I start running through my head, what are some things that I see in this image that I think might give me clues as to what's coming in the problem. I can see this is in uniform circular motion. I can see that I have two different objects, so there's going to be a force of gravity between these different things. I see that I have a radius marked, so that probably means I'll be dealing with a varying radius at some point. Maybe the speed will change, maybe the radius will change. So a variety of different things that I can see just from this diagram. If you have any questions as we move throughout this lesson today that are specifically related to uniform circular motion, be sure to check out the April 10th video that I posted. And if you have any questions about uniform circular motion specifically related to orbits, then you can check out the lesson on the 13th. But we're going to look at the specific problems, the specific application. So this is part A. Give you a minute to look at this. It says in the figure below, draw and label the forces. There's some clues here, or some reminders here. It says don't label the components. And we want to label the forces that are acting on the spacecraft. We're not interested in any forces acting on the Earth. It says when you draw each force, make sure it's represented by a distinct arrow starting at that spacecraft and pointing away from it. So I'm going to give you about 30 seconds. If you didn't do this practice problem, I want you to go ahead and jot this diagram down real quick. And I want you to draw and label the forces acting on this spacecraft. I'll give you about 30 seconds. Okay, go ahead and put your finishing touches on it. And now look back at question A and make sure that you followed their helpful hints. They said to label forces, not components. So I shouldn't have any this sub X or this sub Y. I should only have the actual forces. I also want to have distinct arrows for each force. I want to have them starting at the spacecraft and pointing away from it. Okay, so let's take a look at what the rubric says for this. This part of the problem is actually worth 2 points. It's a nice quick 2 points for you, hopefully. But let's take a look at some things that we typically see for these sort of free body diagrams. Something like this, you might have this on your paper. Now this is a good start, and if you see on the rubric, this is actually going to get you the first point. You've got an arrow directed towards the Earth's center. However, it says to draw and to label the forces. So I haven't labeled this force, so I don't know exactly what force this is you're talking about. So you're not going to get the second point. Now, if we look over here, by simply adding this label, calling it the force of gravity, you've now gotten that second point, which is great. Now, if you notice on the rubric here, it says a maximum of 1 point may be earned if any extraneous forces are present. So let's just say you put something else. Maybe you labeled something like this and you said, oh, well, that's not an extraneous force. I was labeling the velocity vector. Well, the issue is you were supposed to draw and label the forces. And if you put any arrow on this, the reader has to assume that that's a force. So the reader is going to assume that you have labeled this as this is the force of some V. So the force of the velocity or something like that. Okay, this has no place on your free body diagram. We don't want to label velocities, accelerations, only forces go on our free body diagram. So in that particular case, you would have had your 2 points, and then you kept going and you put extra stuff on there, so you're actually only going to get that maximum of 1. So be careful and make sure you're only labeling the forces, nothing extra on your free body diagram. Now, on this upcoming exam, we're not going to be necessarily labeling things, but you could still describe this force. So think about, how could you describe this force? This is your 2-point answer over here. How could you describe this? I'll give you about 15 seconds just in your mind to think about how you could describe this. I would just say the force of gravity directed towards the Earth. There, done. I've just described that force vector. It's the force of gravity directed towards the Earth. And now I've effectively made that free body diagram even without having to draw it. Okay, so something to keep in mind as we prepare for this particular version of our upcoming AP Physics 1 exam. Now, here's some common errors that we see. This is a really common one that showed up. Now, you might think, well, that's silly. Why in the world would I do that? Well, a lot of people oversimplify things, and they get so used to seeing mg as this vector pointing down because we deal with so many things near the surface of the Earth, right? And we just label this mg for that particular object. But that is not appropriate here. That's not the direction of this force vector at all. So don't just overgeneralize and just, oh, I just always put mg down, and oh, maybe a normal force up and maybe a friction force to the side. You have to address each particular situation independently to see what the actual forces are. Okay, there's no sort of shortcut. Oh, if I always put this and always put this. You have to look at each problem individually and see what the actual forces are. Here's another common mistake. People recognize that this is in uniform circular motion, so they know there must be some centripetal acceleration. So there's got to be some force that's causing it. So they'll label Fg, and then they'll say, oh, but we also need a centripetal force. And this force has no place either. What is causing that? What is the thing that's creating that centripetal force? That's Fg. We've already accounted for it. Centripetal force is not an additional new force. It's just the way that the forces that are already acting on it are behaving. They are creating a centripetal acceleration. So Fg is playing that role. There's not an additional force towards the center. Some people added this force, maybe they called it thrust or the forward force of our spaceship. They think, well, if it's going to go around the circle, it's got to have some forward force. Well, that's not true. It needs to have a velocity, but it doesn't need to have a steady force. And in fact, if it did have this forward thrust, then it wouldn't be in a circular orbit anymore. It would start to come off of this orbit. And then finally, we see forces that are directed out and away from this. And the reason why I think people come up with this is a sensation that's sometimes experienced when an object is in uniform circular motion, right? If you're on a ride on the fair and you are an object that's going around in a circle like this, you might feel like you're getting pushed back into your chair or the wall or whatever is holding you into that ride. You might feel like there's something pushing you back, but there's really not. In fact, what's happening is you're trying to go in one direction, and then what's behind you is actually pulling you in. So you do feel the force behind you, but that's actually directed towards the center of the circle. It's actually directed as a center-seeking force. You feel it behind you, right? There's nothing in front of you pushing you away from it. So we don't want to have any forces aimed out away from these objects in circular motion. We're focused on the forces pulling you in. Okay, so there's our free body diagram. Let's move on to part B. We need to derive an equation for the orbital period. So I like to identify what is it that I'm looking for, the orbital period. So capital T period. Now here's a common thing that we see when we look back at at the sample responses, and we looked at student responses in 2018. People have this thought process. They say, well, doesn't the term period only apply to waves? You go, oh, well, no. It does show up one other place. Simple harmonic motion, right? So we've got these two equations for period of a simple pendulum and of a mass spring oscillator. And then you go, aha, I'm real clever. I got this. I'm going to go ahead and say that T doesn't exist because the spacecraft's not in simple harmonic motion or in a wave. Ha! See, I'm not going to fall for these trick questions. So I'll go ahead and scribble something real clever on there and let them know that I caught them with their trick question. Okay, guys, I got to be honest. I got to be really straightforward here. These are not trick questions. Okay, there are no trick questions on the AP exam. Now, are there questions that ask about specific nuances? And that question is designed to see if you recognize one nuance versus another? Absolutely, but those aren't tricks. Those are details, right? Something like this, all right, the question asked me for period. No, there isn't a period because it's not a mass on a spring or it's not a pendulum. No, that's a trick question. Those are not the questions that are on the AP exam. So you've got to figure out, okay, they're asking me about the orbital period. It exists. How do I figure it out? Well, remember, period is just a general term used for a specific length of time to measure a single event, a single occurrence, something that's repetitive. Sure, a pendulum goes back and forth. So that's a repetitive event, so we can measure that time period. Okay. A wave goes through a full cycle. That's a repetitive event, so we can measure that time period. But something orbiting a planet also is a repetitive event, and we can measure that time period from there to there. That's t. To there. That's t again. So let's get on with the actual question. How do we derive this? Notice in blue here, I've highlighted another statement that was on the question itself. It says, if you need to draw anything other than what you've shown on part A, do not add anything to the figure in part A. Now you might be wondering, why is this included in the prompt? What's the big deal? I already answered A. What does it matter if I go ahead and make changes to it? Well, let's just say you got ready to answer this question and you said, all right, the circular path is going to follow this this circumference here. It'll be measured with 2 pi r. I know that I've got the force of gravity on there. I got my 2 points from the free body diagram, and now I'm going to label this V. Well, the problem is you've now just changed your initial diagram, and these readers don't know when you added that V. They don't know if that was you answering part A. So they have to assume that if you've put it up there, that that's part of your answer to part A, and you're going to lose the point. So when they give you these clues, watch out for them. If they tell you do not add anything, they mean it. It's for your own good. It's to help you. So make sure you're following these instructions. Make sure you're following these clues, right? If you need to add something, don't put it in part A. Part A is being graded as its own thing. So the exam writers are trying to help you. They're trying to warn you. Yet time and time again, we see stuff added to that diagram and they end up losing points because it has to be graded as if that was your first free body diagram. So let's get on to the actual derive part. What does derive mean? Here's the College Board's definition. Here's the approach I take. I like to start with some fundamental law, relationship, physics concept. Then I want to apply the specifics to this question, right? Whatever the scenarios in this question, I'm going to apply those specifics. It's not a memorization of different things. It's actually taking what is the scenario that I have in front of me, and how do I apply that to this fundamental law or this relationship or this concept. Then I'm going to make any necessary substitutions. We've got some variables up here. I want to make sure that I'm using those variables so that I meet the requirements of this problem. So let's see what this looks like. Derive an equation for the orbital period. Well, I know that this object is in uniform circular motion, so I'm going to start my derivation with Newton's second law, F equals ma. Now I know it's in circular motion, so this is going to be a centripetal acceleration. So I know that over here, this will be mv squared over r. Now, what's the force? Well, I'm going to go back to my free body diagram. The only force that's acting on this, the force that's keeping it in this circular motion, is going to be the force of gravity. Now, I know that the force of gravity could be calculated with this. This is the mass of the Earth. This is the mass of the spacecraft. I'm using the variables they give me. So I have this here. Now, at this point, I could do some simplification. I can go ahead and cancel out this r with one of these. I can cancel out the mass of the spacecraft on both sides. And what I end up with is v squared equals g m over r. But that's still not in terms of period. So to determine the period, I need to go one step further. I need to look at this actual path. Okay. The speed is going to be a measurement of the distance divided by the time. Well, the distance around that path is 2 pi r, and the time is that period, t. So I'm going to take this is my velocity, and I'm going to plug this in for v squared. So over here on the right, I'm going to have 4 pi squared r squared over t squared. That's this, going in for this, and then squaring it. All of that equals g me over r. Now I'm getting really close. I want to get t by itself. So I'm going to look this r on the left and that r squared on the right. Those are not going to cancel because when I multiply this r up, I'm actually going to end up with r cubed. I'm going to divide by g and me, and then I'll multiply t squared up to the other side. So this whole thing would be equal to t squared. I'm going to go ahead and set t equal to the square root of that. Now, if I look at my rubric, I get points along the way. I get 1 point for using Newton's second law, and so I didn't get the point just for using Newton's second law, but and equating it to the centripetal force. and equating the centripetal force to the gravitational force. So once I've actually applied it to this specific scenario, right? So here's Newton's second law. How does it apply to this problem? Well, now I'm in business and I've got that first point. The second point comes for substituting V for this 2 pi r over t. So recognizing that this is going in a circular path. So once around the circle is 2 pi r, that's the distance divided by the time, that'll be the speed. I need to do that because that's the only way that I can introduce t into my derivation. And then the third point for ending up with a correct expression of t. So let's look at some student samples here. Take a look at this student sample and look at the rubric. What do you think? First point is for equating the centripetal force to the gravitational force. That occurs right here. They got the first point. Now you'll notice they have V written here, but what they've done is they've solved for the orbital speed necessary, but that isn't going to help them get T. And they've got this equation over here, which is not the relationship between V and T. So they're not going to get the second point, and then they don't have a correct algebraic solution for T. This will be 1 out of 3. Let's take a look at this one. We've got the force of gravity, G m1 m2 over r, and then they substitute in their variables. But be careful, right? This should be r squared. But in addition to that, they never even set that equal to the centripetal force. So they didn't get this first point. Now you'll see that they have 2 pi r written here, but that's not going to get the second point because the 2 pi r isn't related to the velocity here. Now, if they had t equals 2 pi r over v, well, then now they've related period and velocity. And then they definitely don't have a final expression for t, so they're not getting any points here. Here's a great solution. They start with Newton's second law that hasn't gotten them the point yet, and they say that the force is going to be Fg. That's great. It's at this point right here where they've finally applied it to the specific scenario and said, hey, that force will create a centripetal acceleration. So now we can get this first part of the derivation. They have to bring something new to the table. You can't just write an equation and hope that you're going to get points in a derivation. You have to set it up and then plug in information from your own problem, from this specific scenario, to then start getting points for actually bringing something new to the table. Here they've put this 2 pi r over t for the velocity, and then they've got the correct expression over here. So this is going to be all 3. So let's move on to part BII. Here we have a second spacecraft with a mass of 2m, but the same radius. So I've changed m, but I have a new radius. So let's take a look at this answer here. It says, is the orbital period of the second spacecraft going to be greater than, less than, or equal to? Now remember, so I'll back up. You remember one of the tips that I recommend is write your little explanation first and then check the box. That way you're not trying to force yourself into answering whatever your hunch was. Instead, you actually go to the physics part first, and then you see, what is my conclusion? Oh, that's my conclusion. Let me check the box. So let's take a look at this response. Orbital speed is based on the square root of g m over r. So the speed is not affected by the m of the spacecraft. That sounds like a good explanation, except for, what are we missing here? We're looking for orbital period, right? So we didn't connect this to the orbital period. We didn't actually answer the question yet. So if you mention the speed, you need to also address the distance too. So I can add to this and I could say, if the speed is the same, which was their first sentence, and the distance is the same, still 2 pi r, then t must be the same. Okay, and now we've got a complete explanation. Be careful, a lot of times people write something and say, wow, that sounds really great. But then they forget, what are you actually asked about? And in this case, they were asked about orbital period. So you need to finish connecting those dots to orbital period. Let's look at another one. Larger spacecraft requires a larger force of gravity to orbit, okay? Fg is proportional to m, so Fg would be larger, okay? So the spacecraft maintains the same orbit, which means it maintains the same speed and t. How does that sound to you? See, they've said some nice things, but have they connected the dots? Have they actually explained why the speed would be the same and why t would be the same? They just said that it is. The first part of this explanation isn't really useful. And then the second, the conclusion statement, doesn't match what they presented. they came up with a conclusion without any evidence. They just explained it is because it is. So you need to make sure that you're actually connecting the dots. So I'm going to make this problem really simple. Let's look back at our equation. We just derived an equation for period. Look, we just derived an equation for t, and now we're asked, how does t change? So let's look at the variables. T is going to be based on 4 and pi, right? These are all just constants. Universal gravitational constant, that's big G, the mass of the Earth. These are all things that are staying the same. So that means that this is really the only variable I need to worry about. So here's my explanation. According to this previous equation, we just derived this equation. Let's use it. T is going to be affected by the mass of the Earth and the radius of the orbit. Both of these are unchanged. So T is not going to be affected by the mass of the spacecraft. So you can double the mass of that spacecraft. It's fine. It's still going to be equal. Period is still going to be equal. Let's look at some other student samples. This one said the increase in mass causes a decrease in T. So if we look at this equation, you need to be careful. They said an increase in mass. Well, the mass that increased was the mass of the spacecraft. We need to be careful with what we're saying. See, in your equation, that was the mass of the Earth. And here we're referencing the mass of the spacecraft. That mass is not part of the equation. Here's a scenario where a student had the wrong equation for T. So they wouldn't have gotten full credit on their derivation, right? This is not a correct expression for T. So they didn't get full credit on their derivation, but they can still get full credit here if they use this equation properly. They say little m is not in the equation, therefore the mass of the spacecraft doesn't affect the orbital period. It's the wrong equation, but they used it properly. Perfect. They can still get this point. Now here are some other scenarios. Here's a totally wrong equation. If you got the wrong equation, but you used it properly, you can still get the points. You just have to make sure that you analyze that equation properly. Here they said T is proportional to little m. So if m doubles, then T would double. Right, so in this particular case, they had the wrong equation for T, but as long as you analyze it properly, right, this part of the problem is not asking you to derive a new equation. It's asking you to analyze the equation that you just derived. You do this type of thing a lot in a QQT style problem. You will either be given an equation or you'll come up with an equation, and then you'll analyze the relationship between these variables. So if you have this equation, you need to analyze that equation, and if you do it properly, you'll still get the correct, or you'll still get the point. So here they said T increases, and they actually get the point, even though the true answer was equal to. Why do they get the point? Because they analyzed their equation correctly. You're not going to lose points again for the wrong equation. That's the equation that you came up with. Now use it. Here's a scenario again, an incorrect equation, but they've already lost the point for deriving that equation incorrectly. As long as you analyze the relationship properly, you can still get that credit. And in this particular case, it was inversely proportional to m, so T would have to decrease as m increased. So this student could get the point because they've analyzed their question properly. Okay, so make sure whatever equation you have, you're using it properly. Now let's go to part C. The spacecraft has moved to a new circular orbit. Okay, so now we were on that orbit, now we're on this one with R2. I want you to think about what changes. Some things are definitely going to change. We've just moved our spacecraft further away, so the force of gravity is going to be different. Now, because the force of gravity is equal to mv squared over r in order to maintain this orbit, that means mv squared over r is going to be different as well. Now, these are equal, and if I analyze this relationship, that's one approach to answering question C. I'd say it's the easier approach. Some other things that are changing, my orbital distance is going to change. 2 pi r is now bigger because I have a different radius. The orbital period will also be different. Remember, the orbital period is based on an r value. So if r changes, that orbital period will change. This is kind of the second approach. I would say this is a little bit trickier. Okay, I'll show you an example for each. Start with number one, or the first approach. It says here, this is the actual question for C, is the speed of the aircraft. Now I've circled this because we're no longer asked about the period. Now we're talking about the speed of the aircraft. So make sure you're aware of which things are being asked. Is the speed of the aircraft going to be, or spacecraft going to be greater than, less than, or equal to the original speed? So this is my relationship for orbital speed. V squared equals gm over r. So while in orbit, V squared is inversely proportional to r. So if r increases, then V must decrease. So it'll be less. Okay, I've taken that relationship between the force of gravity and the centripetal acceleration. So I've set up that g m1 m2 over r squared set equal to mv squared over r, and I can see that v squared equals gm over r. That's the orbital speed for a circular orbit. Okay, we talked about that last week. So I can look at that relationship, say v squared is inversely proportional to r. Okay, you could also say that v is, or you could say that v squared is proportional to 1 over r. Okay, you could also say that v itself is proportional to 1 over the square root of r. You have multiple ways to say this, right? But as long as you recognize this mathematical relationship and then analyze it properly, that if I'm going to decrease, or excuse me, if I'm going to increase r, then this value will have to decrease. Now here's our second approach. Our second approach is a little bit trickier. Some of you may have taken this approach and you tried to compare this new orbital distance to the new orbital period. And that's fine. The problem has been sort of leading you in that direction because you just derived orbital period and then you analyzed your equation for orbital period. So the speed that this thing is going to travel, remember we're asked about the speed, is going to be determined with the total distance, that's 2 pi r. Now this is our new radius, that's fine, right? But our 2 pi r, that circumference, that's going to be our distance traveled, divided by the time, and that time was the equation from earlier in the problem. That's that orbital period. Now I said this one was a little bit trickier because look, you've got r in 2 different places. So to analyze this, you have to be a little bit careful, a little bit more careful. R on the top is raised to a power of 1. R on the bottom of this is cubed, but then it's within a square root. So it's actually raised to the power of 3/2. So this radius right here, the one in the denominator, is going to play a larger role. So decreasing the radius, it's going to decrease both values. Decreasing the radius will decrease the distance. It will also decrease the time, but not by the same factor. Decreasing radius will decrease the time by a larger factor, right? This part down here is going to be affected more. So it's going to decrease the time by a larger factor than it decreases the distance. So my distance is going to, or my radius is going to in distance because of an increase in r. And this is an increase in time because of an increase in r. I'm sorry. So this should say increasing, sorry about this. I'm fixing it. Increasing r will increase, sorry, time by a larger factor than it increases the distance. So the denominator is increased by a larger factor than the numerator. So the overall value will actually be less than before. There we go. I fixed it. Sorry about that. Hey, got to adjust on the fly, right? So here are some student samples. The student sample, they've got this relationship. And then they said in the second orbit, r will increase. Therefore, v will decrease. Now, this is a great explanation. The reason why I circled and underlined these parts is this explanation could be condensed, could be answered a little bit more efficiently. Right? This explanation, this is a briefly explained, it can be done in a sentence or 2. So they could have started with this equation and then written the underlined parts here. In the second orbit, r increases, therefore v decreases. So you can keep things concise and to the point. Here's 2 other explanations. This top one's great. They've got the relationship between v and r. And they say if r increases, then v will decrease. Next one says, as seen in the derived formula. Well, which formula? So my helpful hint here, if you're going to be referencing other things, be specific. Either rewrite the formula. In this case, the person has rewritten a particular formula, or they've written it for the first time in this explanation. But if you're referencing a different formula, maybe it was printed in a different part of the problem. Say the formula in BII or the formula in BI. So be specific which one you're referencing. Now, in this particular case, they're addressing T again, so that didn't even answer the question. We're trying to look for the speed. So let's talk specifically about this problem, but how some pitfalls could kind of derail your attempts at other questions as well. In this particular problem, here's some things that we saw when looking at these, when we were grading them. Here's some common things that the readers saw. Ambiguity, people use the word gravity. How can I improve this? You can almost always improve it by being specific. Are you talking about the force of gravity, or are you talking about the acceleration due to gravity? I typically try and avoid the word gravity on its own. Are you talking again about the force of gravity, or are you talking about the acceleration that's a result of that gravitational field? Right, so is force of gravity or an acceleration due to gravity? The word gravity on its own is a little bit ambiguous because you could be referencing a force or an acceleration, which are two different physical things. In these explanations, we saw a lot of students saying it pushes or it pulls. Anytime in your exam, I talked about this the other day, try to avoid using it. Whatever it is, say what it is. So blank pushes or blank pulls. Now, with this in mind, make sure that whatever you put in that blank, make sure it's an actual force. Right? We saw a lot of student samples where it says the velocity pushes it around the path. Well, velocity doesn't push. It's not a force. It's not capable of pushing. Or we saw a lot of responses where it said the momentum of the spacecraft continues to push it around the circle at the constant speed. Well, momentum doesn't push. Okay, only forces push. So if you're going to tell me that something's pushing or pulling, make sure you tell me what it is, and then make sure that the it you're telling me about is an actual force. Velocities don't push, accelerations don't push, momentums don't push. We also saw a lot of overgeneralizations. Mass doesn't matter. We see this in there briefly explained on a lot of student work. Mass doesn't matter, so blah, 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 blah. Well, I believe mass does matter, right? The mass of the spacecraft canceled. So maybe the mass of the spacecraft is not part of the final derivation, but mass certainly as a big concept certainly matters, right? The mass of the Earth was in all of those equations. So you can't make an overgeneralization and just say mass doesn't matter. Make sure you're specific. You could say the mass of the spacecraft cancels. We also saw a lot of statements, well, there's no gravity in space. Well, that's an overgeneralization. How could we improve that? Well, the gravitational field weakens as you move further from a planet, yes. But that spacecraft is still in the Earth's gravitational field, so there's still gravity. Is that gravitational field as strong as it would be if they were on the surface of the Earth? No, it's weaker, but that's why all of these equations we're working with have R values in them, right? It is location dependent. But to say that there's no gravity in space is a broad overgeneralization, right? The gravitational field will weaken. Now, could we put that spacecraft so far away from the Earth that the gravitational field is effectively zero at that point? And so it would experience no gravitational pull from the Earth? Of course, but not where it's located. And certainly we don't want to use this overgeneralization. There's no gravity in space, right? Lots of gravitational forces in space. That's what keeps all of our planets orbiting the sun, right? So these overgeneralizations, mass doesn't matter, no gravity in space, we want to avoid those things. If you canceled a specific mass in your derivation, then reference that. Some other common errors that we saw on student samples. And these showed up sometimes in the explanations and sometimes on the free body diagrams. A tangential force is required to keep something moving. Well, remember that velocity is going to be tangent to whatever that force is, or perpendicular to the force. It's going to be tangent to the path. So the velocity is going to be tangent to whatever the path is. But that doesn't mean that there's a force aimed in the direction of that velocity. A very common misunderstanding is students believe that if an object is moving, then there has to be a force in that direction, and that's just simply not the case. Something can be moving with a constant speed, and there's no force in that direction. And during uniform circular motion, that's exactly what's happening. We have a velocity that's tangent to that path, but the force is towards the center. Again, people mentioned these forward forces, some sort of thrust. That would have pushed this spacecraft off the circular path. And some people say, well, couldn't that happen? Well, sure, but now you're playing the what if game, and that's not the problem that was presented. The problem that was presented said it's in a uniform circular orbit, or it's in a circular orbit. So we don't have this forward thrust. Some other common errors. The centripetal acceleration makes the spacecraft turn. Accelerations don't make something turn. The fact that it's turning means that there's an acceleration. What's actually making it turn is the force, right? The force is what makes the behavior change. And then the acceleration is the result. And acceleration is a way that we can describe the effect of that force. What's the result? It's the force that's making it turn and then creating that acceleration. Sometimes they mention an outward force, and I talked about this briefly with the free body diagram. You don't want to mention an outward force if something's in a uniform circular motion. Remember, we said this is a sensation that's sometimes felt by an object. I mentioned if you're riding around on a ride at the fair where you're spinning around in circles, and you might feel like you're pushed up against the wall. You feel that extra force there, but really what you're feeling is that wall pushing into you. That wall is pushing towards the center of that path and holding you in uniform circular motion. There's nothing in front of you pushing on you. There's nobody on that ride pushing you with like a little stick or something back into your seat. No, you're completely exposed on the front side, and then your back is up against something, a wall, a chair, something like that. All that force you're feeling is actually back there. You're actually getting pushed from behind, and that's what prevents you from going in a straight line. You get pushed towards the center of that circle, and so you turn, you turn, you turn. In the case of an orbiting planet, that force is coming from that gravitational attraction between the two planets. And then we saw this on the Freebody diagram as well, and it showed up on a lot of our derivations. This is a common pitfall when dealing with any sort of uniform circular motion. People will put the correct forces, maybe it's a tension, maybe it's the force of gravity, depending on what the scenario is, and then they will also put an FC. Well, what's that? Right, if I have a pendulum and there's a tension acting on it, well, then the tension is an identifiable force. mg is an identifiable force. In the case of this planet orbiting, Fg is an identifiable force, but what is Fc? Just a magical additional force? No, remember that Fc, that idea of a centripetal force, is a force that's aimed towards the center. That's going to be one of our other forces or some combination of the actual forces. So whenever you identify forces, make sure you can identify what is the actual cause of that. Right? In the case of Fg, I can identify the cause. It's a gravitational attraction between the spacecraft and the planet. Fc, what is that? There's nothing else there. That gravitational force is a center-seeking force in this scenario, so it will create the centripetal acceleration. There's not an additional Fc that belongs in your analysis or your derivation. All right, let me get you set up with the next exam practice. Tomorrow, Greg is going to be going over the next practice problem. I've got a couple images here. I tried to zoom some of them in, but some are still fairly small. There's going to be 5 screenshots here. Okay, I'm going to go ahead and just kind of mute my videos so that it doesn't block any of this. Go ahead and take a screenshot here. This is going to be your first of 5 quick screenshots for the upcoming practice problem for tomorrow. Here's your second one. Here's your third screenshot. Some space here for you to do the work. The last one, you were going to put stuff on those graphs. Next screenshot. And then the final screenshot. Again, this is for Greg's problem tomorrow. If you missed any of those, feel free to go back once this live session ends in just a minute here. You can feel free to go back and screenshot those. We can also try and get them posted in the lessons folder for you. As always, if you have any questions about today's lesson, feel free to reach out to me. If you have just recently watched any of our older review sessions, feel free to reach out to me with those as well. We appreciate all the feedback we've been getting. We appreciate you guys asking really insightful questions, both from students and from other colleagues. It's been a really positive experience, so we are very grateful for all of you that are watching both live and on recording. If you guys are, some of you are starting to send us pictures of your sample work and asking some questions about that, which is really cool also. Just something to keep in mind if you are doing that, just be careful how you're taking your picture, right? If you're intending to upload a photo for this upcoming exam, you need to make sure that the readers can read your work. So if you're taking a photo, hey, just make sure that you've got good lighting, make sure that your camera is directly over your paper so we can really see what's going on. Make sure you use good contrast with whatever you're writing with, stuff like that. But just some helpful hints. We'll talk some more about specifics of how you're going to be submitting your exam work and things like that as we move forward here. But just kind of a helpful hints, and some of you are starting to show us sample work and asking us questions about that. Just make sure we can read it, because you want to make sure that you're the person grading your actual exam can read it as well. So as always, thanks for watching. Appreciate the feedback. Feel free to reach out to me on Twitter, and look forward to working with you guys again. Greg's going to be here tomorrow, and then I'll be back a little bit later. So have a great afternoon. Thanks again.